Alright, how's it going with you folks? Can you guys see my computer screen? Can you hear my voice and all of that jazz? I actually should probably start this off with, what's going on, my chemistry students? I have no idea why I started all of my classes off like that, but that's the deal that I do. Give me a second. Someone's calling me. 1 second. Hello? Hello? Hey. The keys are they're on the door, aren't they? Let's see. Wait 1 second. Oh no, I have them in my pocket. I went downstairs to grab something out of the car. I'm so sorry. I guess you guys can't go to your thing then today. I'm sorry about that. I had to open up the door to clean out the car a little bit so that way it was going to be clean for the time you guys get home, but I guess I left them in my pocket. Sorry about that. Okay. Alright. Okay, I'll talk to you later. I'm sorry, I'm in class right now. Okay. Sorry. I made a mistake. I left the keys to the car in my pocket. My wife had to go somewhere. Ugh, I'm going to hear about it when I get home. It's just been one of those days, man, I'll tell you. Alright. Okay, so let's get this thing going with what's going on. What am I doing? I'm all disheveled now. Alright. Okay, we're doing stoichiometry. We're doing more stoichiometry. Can you guys hear my voice? Can you guys hear me? Alright, cool. So, we're going to kind of pick up where we left off on chapter 3. Let me kind of tell you what's going on with the class and where everything is at. So, the class looks similar to the quarter 1. In fact, all I did was I copied the the thing from before, but I took out all of the quizzes and all of the homework for quarter 1. So I just put all of that stuff up there for you to reference so you guys can have access to all of the old archives and all of the old stuff. So if you guys wanted to, you guys can go back and review that stuff. Does that make sense? We are going to cover chapter 4 and 5. And ideally, I'd like to get to chapter 10. But to be honest with you, we took a whole quarter to cover 3 chapters, and those are supposed to be the easy chapters. So I don't know if we're going to get through all of this. I'm not hard pressed to get through like a certain amount. I'd like to get through as much as I can, but I realistically think we're going to get it through maybe chapter 7. Chapter 4, definitely. Chapter 5, yeah. I shouldn't say easy ones because those weren't the easy ones. I take that back. I apologize. Those were supposed to be the fundamental ones. So, the stuff we're going to be covering, actually, to be honest with you, I think is actually easier, but it requires a lot of your understanding of chapter 1 and 2 and 3 in order to do them. You notice how chapter 3, when we were doing stoichiometry and that kind of stuff, we really, we covered over the stuff about, oh, I'm sorry. I don't know why there's only one chance for chapter 4. All right. But you notice how when we did chapter 3 stuff, we used a lot of the conversion factors? And so since we did that, a lot of this new chapter is going to be based off of the old stuff. So now I can see Bradley freaking out right now and saying, oh no, that means we're going to have to do moles and stuff like that. Yes, Bradley, we are going to have to come back to moles. Those are important. And Francis, I'm sorry, I made a mistake. It is, I think I'm giving you guys 5 attempts on all of your homeworks from now on. So if it doesn't say 5 attempts, let me know. So I'm trying to give you guys more chances. And I'm trying to give you folks more time as well. It's not going to be as crazy. For algebra, I cannot push things back, but for chemistry, I feel like I'm allowed to. All right. So this chapter 4 talks about dissolving things in water, and water is the most common solvent that we would use. It's one of the most important substances to us people on Earth because it keeps us alive, but it also helps us to moderate the Earth's temperature or cool the engine or nuclear power plants and all of that kind of stuff, which is kind of important to keeping us alive. Um, and a lot of creatures use the water as food, or well, we do too as well. One of the most important thing about water is we can use it to dissolve things, and that has to do with how the water molecule is actually structured. Water is actually bent in a V-shaped looking molecule. It has a bigger oxygen right in the middle, and it has two H's. Now, I'm not going to go through the math of this, but what's interesting is you can actually go in and calculate out exactly, I think I talked to you guys about like electron interactions and how many protons and how many electrons. And you can actually go in and calculate out how far apart the angle that is going to occur between these two water molecules based off of like the repulsive forces and all of that kind of stuff. And when you go through that, and that's kind of an advanced like quantum mechanics thing, but when you go through that, it's 105 degrees. And that is the end of your calculations that you need to do in high school chemistry at least. So I'm not going to make you calculate that out at all. I'm just going to tell you it's 105 degrees and let you know that it is able to be calculated. In fact, it's even not really that like crazy as far as doing the calculation. We cool? I'm just not going to do it for you, nor do I feel like you guys want to see it. All right. But once you have that information, you know that it's a polar molecule. And let's see, what else about water do I want to tell you? It's got 105 degrees. Let's see. They're very important to recognize when an ionic substance of salts dissolves in water. They break up into individual cations and anions. So, for example, if I have a salt called ammonium nitrate, which is actually some of the salts that I use with my 7th graders when we were doing testing for their project. But ammonium nitrate is NH4NO3. Now, the anion, which is what was that one again? That was the negative one, and the cation, which is the positive one. Let's write down NH4O3. NH4O3. Am I recording this? I better be. Yeah. All right. NH4O3. Or, I'm sorry. It's NH4NO3. All right. NH4NO3. You folks have memorized what NH4 is. That's ammonia, right? And I think I even gave you guys the initiative to memorize the charge on it is NH4+. That would mean that the cation is ammonia, and the anion is NO3 minus. And when I dissolve this salt in water, it will give me these two. It will break down these ions. It will break it into ammonia or ammonium cation and NO3, which is nitrate, anion. Does that make sense to you? And then when we write this in an equation, we usually write this like this. NH4 NO3 yields NH4 AQ plus NO3 negative AQ. And what AQ stands for is aqueous. I think that's how you spell it, aqueous. It means it's a solution of something. It's like a liquid. Audio check, 1, 2. Can you guys hear me still? What AQ stands for is it's the aqueous solution. So if it were a solid, I would put S. If it were a liquid, I would put this. If it's a gas, I would put a G. But if it's an aqueous solution, that would be AQ. Do they have a better definition for it? Yeah. AQ designates that the ions are hydrated by unspecified numbers of water molecules. So what it's saying is AQ is not just a liquid, but it's saying that it's a solid that was dissolved into a liquid, into some water. But I don't tell you exactly how much water. It just tells you, it's that water was present. So, how well can a salt dissolve into water? Well, the salt to do that, we would refer to what is called the solubility, and it's talking about how the ability for something to dissolve into or turn into ions into when it's in the presence of water, and that varies greatly. For example, your silver chloride is only very slightly soluble, whereas ammonium nitrate is very soluble. And that actually has to do with the electronegativity. So that thing that you guys covered in your midterm exam, that's actually what it has to do with. All right, so let's talk about this one. Here we go. Okay, I want to do some examples. I want to get to molarity. Molarity is actually pretty straightforward and easier to talk about. All right, I'm not going to cover weak electrolytes or strong electrolytes. I don't necessarily think. I mean, that is important, but it's not something I'll let you guys read up on that. All right, composition of solutions. All right, so let's talk about something you're more familiar with. Do you guys ever drink orange juice? Yes. No, you don't? What? Really? Oh, okay. How come you don't drink orange juice? Oh, you can't have sugar. Okay. All right. I'm sorry. Fructose. All right, fine. Well, I guess my example that I had in the top of my head was orange juice or fruit punch or apple juice, but that doesn't sound like it's anything up your alley. Well, for the rest of the class, I'm sorry, Bradley. I don't mean to single you out there, but do you guys have orange juice at home? And here's my question. How do you make your orange juice? Bradley doesn't make orange juice, but how do you guys actually get, like, do you guys get fresh oranges and squeeze it? See, because what I do in my house is I get like the concentrated orange juice in a little, it's not even a jar, it's almost like a cardboard cylinder. It looks like a cardboard can, and you pull off the top, and it's like frozen orange concentrate. And then I pour it into there, and I add in water. Right? Do you guys do that? Or do you make it straight from like pure oranges that I picked and I grated with my teeth and strained it? All right. Bradley's the only one talking to me. Come on. Maria. Who else is there? Sophia. Francis. Talk to me. All right, we buy our orange juice. You just buy it from Costco. Okay, all right. But can you imagine what I'm talking about? Where you're like, you have to make, or if you guys got to go make the fruit punch for the party, right? You have like the pure concentrate, and then you pour in some water to kind of dilute it a little bit. Yeah, all right, good. It's the red, yeah, or Kool-Aid. Kool-Aid, that's a good one. All right. Now, I'll be honest with you. Growing up, my mom is really cheap, and what she does is she'll take like maybe they say we recommend that you make the orange juice or the fruit punch with 1 cup of orange juice or 1 cup of fruit punch concentrate and put in 3 cups of 3 cups of like water, right? And what my mom does is she'll take like a third of the packet of Kool-Aid, or she'll take like a teaspoon of the stuff, and basically make disgusting reddish water, like water that kind of has a pink hue to it. You know what I mean? All right. Yeah, no. We're talking about orange juice. All right. So it's pretty gross water. That's what my mom makes. And so what I guess the thing is, all we're going to talk about today is the molarity of something. And what it really is talking about is it's talking about the scientific way of approaching how to find the concentration of an acid or the concentration of something. So the units of it is going to be, it's going to be similar to grams per mole, or not grams per mole, but liter. But remember, we don't ever use, well, we don't talk about the grams as much as we talk about, if we're talking about the molarity, you would think that it's moles per liter. And Brad's like, oh man, here we go again with the moles. Yes, Bradley, I apologize. We deal in moles. So it's M-O-L-E or M-O-L, depending on, how you abbreviate the thing. But we talk about the molarity of something is how many moles per liter that you have. And so it's basically talking about the concentration of your substance. If you have a lot of moles for a small amount of liters, then your molarity or your concentration is really high. And your orange juice or your fruit punch is going to be very dark. And that's the good tasting one. Whereas if you put in a lot of water in the thing and you increase the bottom over here, that's going to make the molarity go down. And hence you're going to have that gross, slightly orange or slightly pink water that you don't want to drink because my mom is too cheap to actually use the whole packet of Kool-Aid. Apparently, this has scarred me in my childhood, as you guys can tell. We cool? All right, so let's do a few example problems. Yes, my mom would use less moles per liter than advised. Of course, I don't think she ever calculated things in moles, but whatever. All right, so check this out. If I have 11.5 grams of NaOH, and I want to, and I put it in 1.5 liters of solution. So, 11.5 grams of NaOH. And I want to put it in, I'll draw my solution. This is 1.5 liters of water, or liquid. Got it? What is the molarity of that? Okay, so first thing is we have grams of NaOH, but what we don't have is moles of NaOH. So to do that, we're going to have to go back to chapter 3 and figure out, well, what is the molar mass of NaOH? You guys have done this before. We've covered this. Let's look up the periodic table. What is Na, by the way? I don't know it off the top of my head. Na is how many grams per mole? Sodium, yeah, sodium. Somebody look it up for me, please. If not, I'll look it up on my own. I guess I'm looking it up on my own. What? What is this? All right, here we go. Na is 22.990. Got it. 22.990. O, I already know. That's 16. And H is 1.008 grams. Bradley, can you be my calculator guy? All right, I want you to add all these numbers up. What does that equal to? Too late. I already did it. 48.99. Is that correct? Yeah, 48.998. Yes, I am recording this, and actually, I will probably be finishing off in the next 20 minutes. All right, so this is the molar mass of NaOH. So if you told me this is how many grams per mole you have. So if we started off with 11.5 grams of NaOH, and I want to use this conversion factor to figure out how many moles. Let me just double check to see if I'm doing the right problem. Yeah, NaOH, there we go. And then what I do is I take that number and I divide it by 1.5 liters. And this will give me the molarity of my thing. So, I'm sorry. What is 11.5 grams of this substance? Let me just double check something. Yeah. All right, we're good. What is 11.5 divided by 48.998 divided by 1.5? And I don't know how to do that off the top of my head. I'm waiting for Bradley. Oh, no. What is 11.5 divided by 48.998? Divide that by 1.5. Anyone else can answer it. Maria, if you want, you can answer it too, please. Gosh, I guess I'll do it on my own then, huh? 11.5 divided by 48.998 divided by 1.5. 0.1564. You guys awake? All right, 0.1564. And this is actually moles per liter, but since it's molarity, we actually say 0.1564. Huh, why'd you guys get a different answer? Well, I guess we got close. We actually say use the symbol M, capital M, which stands for molarity. Which actually, I'm wondering, there's a problem here, is why is my NaOH so different from theirs? Huh, I don't know why they got such a different answer. I think that one of the things they're doing is they have NaOH. What is the moles of NaOH? Oh, they did this wrong. It's not 40 grams per mole, it's 48.98. Huh. I guess the book got it wrong. All right. Okay, let's try this one. If I have 1.56 grams of HCl, of gaseous HCl, that's interesting, and I want to figure out what how much of this hydrochloric gas should I dissolve in water to make 26.8 milliliters of solution? All right, let's figure out something real quick. What is Cl? Chlorine is 35.45. So HCl is 1.008 grams per mole plus 35 point, did I say 5? Oh, 45. 45 grams per mole. What I'm doing is I'm doing the standard, finding the molarity, or the molar mass of the HCl, which comes out to be 36.458 grams per mole. If you add these two together, that's what you get. You can tell me if I'm wrong. Please, please forgive me if I'm doing this wrong in my head, because I'm doing it in my head. You guys are the ones with the calculators. Hopefully, you guys can go faster than me on this one. Now, what did the original problem say? They wanted 1.56 grams of HCl. So what we need to do is, they told us how much HCl, how much hydrochloric acid they have in grams, but what we want to know is how much moles we're dealing with here. So apparently, there is, for every one mole of HCl, it weighs 36.458 grams. Right? So this cancels out with that. We're left with moles of HCl, and that's good. So, what is 1.56 divided by 36.458? Bradley? You got the calculator? Maria, you too? All right, there we go. Thanks. 0.0427 moles of HCl. Now, if we want to find, this is how many moles of HCl we're dealing with here. If we want to find the molarity, all we got to do is take this many moles and divide it by 26.8. 26.8 milliliters. Everyone agree? Yes, thank you, Bradley. I actually, it's funny. I almost try to trick you so many times that every time I say everyone agree, I almost feel like you guys immediately think, no, I don't agree. You're trying to trick us. Exactly. If I'm talking about molarity, I want moles per liters, not moles per milliliters. That throws my calculation off. So what I need to do is actually, it's not 26.8 milliliters, it's 0.0424 moles divided by, let's see, 0.0268 liters. Does that make sense? And that gives you the correct units for molarity, which ends up being what? Is that what your answer is? It's 0.2? Really? Seems like it would be more like 2. What is 0.0424 divided by 0.0268? All right. 0.1582. That seems a little off. Hold on, let me see this. I mean, you're probably right, but 0.0242 divided by 0.0268. 0.9. 0.9029. How come we're all getting different answers here? Is my calculator wrong? Oh, I'm sorry. It's 424. Sorry. Answer is 1.582. Yes, there we go. I'm sorry. So, the answer is 1.582 molarity. Moles per liter. Ayo. Yeah, that's it. Good. Good. And that's molar mass, really. I mean, not molar mass, that's molarity. That's how you do it. It's pretty straightforward. Okay. Let's try this one. This one's kind of crazy. All right. Give the concentration of the following ions in each solution. So, I have 0.5 molarity cobalt nitrate. Right? I have 0.5 molarity cobalt nitrate. And I want to figure out the molarity of the ions of cobalt nitrate. So, we go to cobalt nitrate. So if I'm starting off with 0.5 molarity of cobalt nitrate, was it NO3? I think it was NO3. It was cobalt NO3 2. Okay. I know that cobalt nitrate will actually dissolve into cobalt ion and nitrate ion. I know that NO3 is actually NO3 minus, right? If it needs to balance this thing over here, then this cobalt actually has to be plus 2. Because there's 2 nitrate ions that I'm dealing with. I just broke this thing down. Got it? So 1 mole of this combined substance, it consists of 1 mole of this and 2 moles of this. Of 1 mole of cobalt 2, or cobalt positive 2 ion, and 2 moles of nitrate ions. Got it? So, if they want us to figure out, let's see, if they want us to figure out how many ions go in, or what is the molarity for each ion, well, this thing, to yield this thing as 0.5 molarity, I have to have one. What is the best way to show you how to do this? Okay. I know that if I start off with 0.5 moles of CONO3 2, got it? Then how many moles of ion will I have if I'm talking about cobalt? So this would be 1 mole of CONO3 2 for every 1 mole of cobalt ion. So, what's 0.5 times 1 times 1? That's simply 0.5. And that is the molarity. Oh, man, my handwriting is getting terrible. That is the molarity of the cobalt ion that I have. Now, if I'm talking about the NO3, the nitrates, then for every 0.5 moles of cobalt NO3, cobalt nitrate that I have, then converting that, I know that using this equation up here, I know that 1 mole of CONO3 gives me 2 moles of NO3 minus. Just using this as kind of my conversion factor. So what's 0.5 times 2? This is 1.0 mole of NO3. So what is the concentration of ammonia or of nitrate ion that I have to make this? Well, I have to have 1 mole or 1 molarity of NO3 ion and 0.5 molarity of cobalt ion. That's it. Does that make sense? The ion part is a little bit different because you actually didn't have to convert it using a molar mass or anything. This is where we're actually going back to the equation and using that to help us get these conversion factors. Why did I put which numbers are you talking about? Oh, you're talking about this, like this fraction, like that? Oh, okay. Well, it's because, first of all, I taught you guys about balanced equations, right? And we did a kind of a lab on balancing these equations out. All right. Whenever I have a balanced equation, now what I have up here is a balanced equation. Do you see it? It's right there. We can use that balanced equation to tell us, because this is telling us 1 mole of this is going to yield 1 mole of this and 2 moles of this. So we can use that balanced equation to kind of help us with converting to NO3, because what I want to do is it's the same as a regular conversion. I want to cancel out this and this. Does that make sense to you? So I can refer, so when I want to figure out how many moles of NO3 is yielded if I have 1 mole of cobalt nitrate, then I refer to my balanced equation, which is up top. And apparently, if you put in 1 mole of cobalt nitrate, it will yield out 2 moles of NO3, of nitrate. Does that make sense? All right. Why are they charged? Is that what you're asking? Like this right here? Why are the charges on there? Oh, okay. It's because we're talking about ions. Remember, ions have a different amount of electrons than what it normally has. So we're talking about breaking this cobalt nitrate, CONO3, 2. We know that cobalt actually likes to have, if you look at the periodic table, where is cobalt? Let's see. Oh, well, we know that NO3 is actually a -1. Why ions not the stable element? Well, they're basically saying that your when you put this inside of a solution, it will dissolve into an aqueous solution. Yeah, I know where cobalt is, but it doesn't actually give me a good indication as to why it's +2, because it's kind of in this weird area. I think I gave this to you in chapter 3. We can look up a table and see that cobalt normally makes, I think, either a +3 or a +2 ion. In this case, it's a +2. All right, concentration and volume. Let's try this. All right, I guess I'll do one more example problem and then I'll let you guys go. Is that cool? Someone's got to leave at 12 or 3:30. Someone's got to leave at 2:45. I'm fine with that. I'll finish by then. All right, let's try this one. Typical blood serum is about 0.14 molarity of sodium chloride. So when my wife went into the hospital, they gave her like salt water, and like as a part of the blood serum. And in order to make that salt water, you need to have a certain molarity, a certain concentration of salt in the water. And so that's kind of what we're talking about here. Got it? So what we want to find is what volume of blood contains 0.1 milligram of NaCl. So your blood actually, the blood serum that we have is actually, how much blood serum will I need to have if I want to extract out of it, say that I extracted it by maybe like evaporating it and taking the the salt crystals that are actually left over, how much blood would I need to take if I wanted to get 1 milligram of salt? That's kind of gross. It sounds like a vampire story, but whatever. Let's try it. All right. So check this out. We know, what do we know about this thing? We know that we have 0.14 moles of NaCl for every liter of NaCl. That's the molarity of this thing. Another way to write that is 0.14 m NaCl. Moles per liter and m, that's the same equation. We're talking about we're talking about 1 milligram, which is actually 0.001 grams, if I'm not mistaken. Yeah. Okay. So here's what I would do. I would start off with my 0.001 grams of NaCl that I want to try to get. And then I want to figure out, well, how many moles of that is how many moles does 1 milligram represent? In order to do that, I would figure out, well, what is the conversion factor of NaCl? Na is, what did we say that was? That was like 22.990, right? 22.990. 22.990, and Cl was 35.45. So what is NaCl? What is the molar mass of NaCl? It's 22.990 plus 35.45. And what do you get? 58.44. Okay, so apparently the molar mass of NaCl is 58.44 grams for every 1 mole of that stuff. So what I want to do is I want to use this as a conversion factor, and I want to convert it like this. I'm going to put the 58.44 grams on the bottom to cancel out with the grams on top. And I'll put my 1 mole of NaCl over here. So what is 0.001 divided by 58.44? All right, that would be 1.7111 times 10 to the negative, let's see, 1, 2, 3, 4, 5. 5 moles of NaCl. Not a whole lot of moles of NaCl. Okay, I'm fine with that. All right, this tells me how many moles of NaCl, but how much blood is needed in order to get that many moles of NaCl? I would imagine not a whole lot of blood, because that's a little bit of moles. So I'm going to use this as a conversion factor right here. 111 times 10 to the negative 5 moles of NaCl. And I'm converting it using that conversion factor. So I know that there's 0.14 moles of NaCl for every 1 liter of NaCl, or a liter of blood serum. So do me a favor, what is that answer, Maria, divided by 0.14? What is the answer you got divided by 0.14? And again, to be honest with you, all this is just conversion factors. I'm just using this to convert, I'm using the molar mass to convert something. All right, So Maria got 0.000122, or 1.222 times 10 to the negative 4 liters, which is, I think, 1.222 times 10 to the negative 1 milliliters, or 0.12 milliliters. So apparently, 0.12 milliliters of blood serum contains 1 milligram of salt. That's not a whole lot of blood. But then again, that's not a whole lot of salt. So it's like 1,000th of a paperclip worth of salt. Is that what the answer they got? That is 1.2 times 10 to the negative 4 liters of solution. So 0.12 milliliters of blood contains 1 milligram of pure salt. Blah. Blah. All right, here we go. So, you know what? I'm going to cover the rest of this later on. But anyway, that's how you do molarity. I don't think molarity is that bad, to be honest with you. All right. How's your brains? Your brains all right? That wasn't that bad. That's really easy. Yeah, I'll be honest with you, Bradley, when we get to chapter 5, it's actually going to get easier, I think. Not easier. I mean, you say this is really easy, but it's because you know how to do conversion factors really well. Like, you wouldn't say this is easy if you didn't understand why I was putting the 58.44 on the bottom, or why I put the 0.14 moles on the bottom. See, that was all chapter 2 and chapter 3. So until you understood that, you couldn't really get that. So I can't really say this is easier than the previous chapters. I guess it's easier since you understood the previous chapters. And also, your teacher did a great job of presenting it. Yeah, I don't know. All right. I'll talk to you later. That's class for today.